James Clerk Maxwell's crowning achievement in electromagnetism was showing the unification of electricity and magnetism, and then predicting the existence of electromagnetic waves. Unfortunately, he didn't live to see the experimental verification of his amazing theory. That was done in the 1880s by a man named Heinrich Hertz. And Heinrich Hertz did this by creating essentially an LC circuit. So he has an induction coil to provide the magnetic field, and he has two spherical charged balls that provide the electric field. Those act as a capacitor. And if I have a magnetic field causing an electric field, and then a changing electric field causing a magnetic field as the capacitor discharges, and so on and so forth, what I'm going to create then is a wave that gets transmitted through space, an electromagnetic wave. At some distance across the room, he's got the same configuration for a capacitor, and what should happen is, if the frequency is just right in this disturbance from the transmitter, it should be received by the receiver, and you should get a spark between the spherical balls of the receiving capacitor. And that's exactly what happened. And so what he was able to do then, he was the first person to produce electromagnetic waves in the laboratory. So the results are, of course, that you get the sparks in the gap of the receiving electrodes. In addition, he did subsequent experiments to show that this radiation showed other wave properties like interference, diffraction, reflection, refraction, and polarization. He also measured the speed of the radiation, and of course, as we would expect, it traveled at the speed of light. So this was a crowning verification of Maxwell's theory of electromagnetism. Well, there are some consequences of this, as you might imagine. What I'd like to do is talk a little bit about some simpler versions of electromagnetic waves and look at how they behave. So for example, let's start today with plain electromagnetic waves, something very simple. A nice solution to that would be a wave that travels in this way. Suppose I have a direction of propagation in the x direction, so that's the way the wave is, the disturbance is propagating. And that's going to be caused by an electric field, a time-varying electric field in the y direction, and a time-varying magnetic field in the z direction. So we have three vectors that are mutually perpendicular. Oftentimes we use the vector k to indicate a wave number, wave vector, the direction of propagation. In this case, that's moving in the x direction. The electric field is in the y direction, and the magnetic field is in the z direction. If you remember our discussion about waves before, we noticed that light then or electromagnetic radiation is a transverse wave, because the direction of propagation is perpendicular to both directions of oscillation of the electric and the magnetic field. So that's kind of interesting. Let's once again assume we're in empty space, so we've got no charges, we've got no currents, and then Ampere's law becomes B dot ds is equal to epsilon naught mu naught times the derivative of the electric flux with respect to time. When I solve this equation, I'm going to find what I will end up with are what we call plane wave solutions, such that the electric field can be written as some amplitude E max times the cosine of kx minus omega t. The magnetic field similarly can be written as B max cosine of kx minus omega t. Omega, of course, is 2 pi times the frequency of the electromagnetic wave. The frequency times the wavelength will give me the speed of light. I can also write that as omega over the wave number k. K, by the way, we also write as 2 pi over lambda. Oftentimes wave equations will utilize k's and omegas rather than frequencies and wavelengths. Notice if we take the partials with respect to the above equations, we take d dx, then I'm going to get minus k times E max times the sine kx minus omega t. Similarly for magnetic field, I can get dB dt is equal to minus dB is omega times B max times the sine of kx minus omega t. Therefore, this being the case, I can write the following. I can write the ratio of E max over B max is simply equal to the speed of light, which would be equal to any value of E over B at the same time. This is a very nice, simple electromagnetic wave equation, what we call a plane wave. And at every instant of time, the ratio of the electric field to the magnetic field will always be the speed of light. It's also interesting to look at some of the, what we would normally call mechanical properties of electromagnetic waves. So we might talk about things like energy and momentum. We might even talk about the pressure of an electromagnetic wave. Let's look at that carefully. What I want to do first is introduce a new vector called the Poynting vector. Not Poynting, although it's very suggestive about radiation pointing. It's actually named after French scientist Poynting. That's going to be equal to 1 over mu naught times the cross product of the electric and the magnetic field. This describes the rate of flow of energy in an electromagnetic wave. Poynting vector comes from a cross product of E and B. For a plane wave, E and B are perpendicular, and therefore my Poynting vector is very simple. E cross B, of course, the sine of 90 is 1, so E cross B just becomes E times B, and very simply I get my Poynting vector is just EB divided by mu naught, or since I can write E as C times B, I can also write my Poynting vector as C times B squared over mu naught. For electromagnetic radiation, oftentimes we like to talk about an intensity of a wave or a radiance. And a radiance or intensity we define as the average Poynting vector over one cycle. So time average of the Poynting vector over one or maybe more cycles. Notice that the time average of the cosine term squared, cosine squared of kx minus omega t, always gives us a half. So very nicely I can write my intensity or radiance of this electromagnetic wave as E max times B max divided by 2 mu naught. The 2 comes from the average of the kx minus omega t, cosine of that squared over one cycle or more cycles. I can also write it in terms of just the E field, E max squared over 2 mu naught c, or in terms of the B field as C B squared max over 2 mu naught. So those are nice expressions. This tells me intensity is a measure of how much radiation per time, or I should say, how much energy per time per square meter. That's what intensity or radiance is. So it's energy per square meter per second. Okay, it's like, or if you like, a watt per square meter. That's intensity or radiance. And remember, we used to write the energy density for an electric field as 1/2 epsilon naught E squared. Similarly for B, we used to write the energy density for the magnetic field as B squared over 2 mu naught in a similar way. But since the energy density for both E and B vary in time, and C, don't forget CB is equal to E, it has to be that the energy densities are equal to one another. And I can say, okay, so 1/2 epsilon naught E squared has to be equal to 1 over 2 mu naught times B squared. So this is a very nice expression. And what that means is that the total instantaneous energy density, if I have both E and B, is just the sum of both the energy density for the electric field and the energy density for the magnetic field. Very nice, total instantaneous energy density. If I want to find the average, I have to cycle over one or more waves. Remember, we get a factor of 1/2, and so I'm going to get an average energy density of 1/2 epsilon naught E max squared, or conversely, B squared max over 2 mu naught. So another way of saying all of this is that my intensity can be written as the average Poynting vector, but I can also write it as C times the average energy density. All of those things work nicely. Let's do a nice example of this, very simple example, where we can talk about what is the, suppose I have a point source. So a point source radiating in space, that would radiate in all 4 pi steer radians outward. Let's say I have a power output of 800 watts, and I want to find the maximum electric field, the maximum magnetic field at R equal to 3.5 meters. Okay? Well, the intensity I could write as the average power divided by 4 pi r squared. That I could write as E max squared over 2 mu naught C. If I want to solve this for E max, I'm given, I know the power average, I know R, I know mu naught and C. Therefore, if I want to solve for E max, just move the terms around, and I'm going to get 62.6 volts per meter, or joules per coulomb if you like. My magnetic field, my maximum magnetic field is just that, divided by the speed of light. And that would give me 1.73 times 10 to the minus 8 Tesla. I'm sorry, 2.09 times 10 to the minus 7 Tesla. If I want to know my energy density, I can write that as my maximum magnetic field squared over 2 mu naught, and that would give me 1.73 times 10 to the minus 8 joules per square meter. I'm sorry, joules per cubic meter, it's an energy density. So these are nice ways of looking at the energy and intensity of an electromagnetic wave. A couple of other physical properties that we might like to look at before we finish would be things like the momentum of an electromagnetic wave and the pressure associated with the wave. So in that case, we might think about how a wave would transport momentum P. I could write that as equal to the energy of the electromagnetic wave divided by C. I'm using E here as energy, not as electric field, scalar. So as momentum is absorbed by a surface, there's going to be pressure also exerted on that surface. So first thing, we know that the momentum is going to be equal to the energy divided by the speed of light. I can write the pressure, capital P, as a force per unit area. And in this case, I can write that as 1 over the area times the derivative of pressure, time derivative of pressure. And I can write that then as 1 over c times the derivative of the energy of the wave with respect to t. Put it in terms of the Poynting vector. My Poynting vector then is dE electromagnetic dt times 1 over the area. That being the case, I can then say that the pressure associated with that electromagnetic wave is the Poynting vector divided by the speed of light. This is for a perfect absorber. If I have a perfect reflector, on the other hand, the pressure is associated with 2s divided by the speed of light for a perfect reflector. For example, the radiation pressure for sunlight, just to give you an idea, is equal to something like 5 times 10 to the minus 6 newtons per square meter. So we can associate with electromagnetic radiation a pressure, a momentum, and an energy as well. That brings me to the last part of the course. This is one that is probably familiar to many people. This is how do we examine the waves that comprise the electromagnetic spectrum. And to do that, let's go to the slides. We can talk about, we have 7 types of electromagnetic waves that make up the electromagnetic spectrum. There's not really a sharp division in frequency, it's more in how they're produced that enables us to distinguish between the types of electromagnetic radiation. And let's look at the spectrum. I think that's kind of an interesting thing to do. This is probably familiar to you from earlier courses. But we have basically 4 waves. We have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Those are the 4 types of electromagnetic radiation. We can separate them either in terms of wavelength, or in terms of frequency, or in terms of energy, where in the case of the energy of an electromagnetic wave, that's equal to Planck's constant times the frequency. Planck's constant is 6.26 times 10 to the minus 34 joule seconds. And so that would enable us to calculate the energy of a particular type of electromagnetic wave. We can look at them individually. Radio waves go from about 10 to the 4th meters to 1/10 of a meter. And of course, they're used in radio and television communication systems. Microwaves, slightly shorter wavelengths, used in radar, also used in cooking and other things. Infrared is basically manifests itself as heat. They're incorrectly called heat waves. They're not heat waves, but they are produced by hot objects. All of us, every one of us, radiates electromagnetic radiation in the infrared spectrum. The visible spectrum is kind of an interesting one. It's what we see with our eyes, the Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet wavelengths. It's a very, very small part of the spectrum. We're most sensitive to the yellow-green light at about 550 nanometers. But the interesting thing to remember about this is, in the scheme of things, if I were to look at the electromagnetic spectrum as all the 88 keys on the piano, the visible spectrum would only encompass middle C, basically. So while it's important to us because those are the wavelengths that we can see, it is a very, very tiny portion of the electromagnetic spectrum in and of itself. The range in visible spectrum is about 700 nanometers. That's red to about 400 nanometers. That's violet. Now we can see kind of how it breaks down in these wavelength ranges in nanometers. Then we have ultraviolet light that comes from the sun, of course. That's one source of ultraviolet light. Most of the light is absorbed in the stratosphere by ozone. A little bit of ultraviolet provides us with vitamin D, which is good, but it's best not to get very much from the sun, of course. Then beyond that are X-rays. They're used basically in diagnostics and some therapies as well. Those are very, very dangerous. They're very high energy and short wavelength. Typically, X-rays arise from electronic transitions in materials, as opposed to the final type of radiation, gamma rays. Gamma rays and X-rays sometimes overlap in terms of frequency, but gamma rays are produced by nuclear transitions instead of electronic transitions in the atom. Gamma rays tend to have the smallest wavelengths, shortest wavelengths, and are the highest energy. They're used in all kinds of particle physics experiments and so on, or come as a result of that. But in general, they are extremely dangerous, and you don't want to spend much time with them. Finally, we use the electromagnetic spectrum to look at signals from space. For example, I can look at the Crab Nebula, beautiful astronomical entity, and I can see that it emits all kinds of electromagnetic radiation, X-rays, visible light, radio waves, infrared waves, and so on. And of course, that's the way astronomers learn so much about what's going on in outer space. Well, that brings us to the conclusion of this lecture and all the lectures for this course. At this time, I'd like to give my thanks to my wife and my son for doing the video for these portions of the lectures. I hope that you'll find them useful and at least a little bit interesting. And I hope that you will continue to study electromagnetic radiation and take future courses in physics. You might notice that the shirt I'm wearing is a rather interesting equation. It's the Dirac equation. It's part of quantum electrodynamics, which I hope all of you will study sometime in the future. This course in electricity and magnetism was probably the first step along the way. Thank you. Please be well and be safe.